I am definitely not muted. Okay. I'll just wait till we're back. Okay. Hopefully that is enough to resolve it. All right. So, so this material, 7.5, not on the midterm, but it is the next day. So we'll get that out of the way. And I think that's the last topic. Let me check. Oh, yes, it is. It is the last topic I'm covering from this chapter 7 on polynomial interpolation. Coming up after that will be chapter 9, numerical differentiation and integration. Okay. So, all along, we've been assuming in polynomial interpolation that the x values for our data points are distinct. So, what happens if they're not? So what we can do is, if we have two distinct x values, xi and xi plus 1, and these are our y values, and we let one of them approach the other one. So I'm taking the limit as xi plus 1 approaches xi, and then the corresponding y values would also approach. And if we think of our y values as coming from some function f of x, then what happens is the in the limit, of course, we're going to get the derivative. But the thing is, these y values are also values of the polynomial Pn of x that has to agree with f of x at these x values. So, so this difference quotient is therefore converging to the derivative of the interpolating polynomial. So in other words, as x values approach each other, not only do they match values of the function at these points, they will also match the derivative at that point. So this leads to what is known as osculatory interpolation, where you are fitting not just the values of a function at select points, but also certain derivatives. And the term osculatory comes from the Latin word osculare, which means to kiss, from the 2 points converging to each other. All right. So, so I'm going to give you an example of osculatory interpolation, where we have just two distinct x values, x0 and x1. So what we have here is what we would normally have in polynomial interpolation, that your interpolating polynomial p has to match the y values at x0 and x1. But now I have two additional conditions. So p prime only at x0 must equal some given value z0, that's the derivative of f. And then the second derivative at x0 must match this value, that is at double prime at x0. So because I'm requiring 3 conditions to be true at x0 and 1 condition to be true at x1, that's a total of 4 conditions. That's 4 coefficients that you're able to set. So your polynomial must be of degree at least 3. As we've been seeing anyway, the degree should be 1 less than the number of conditions that you need to satisfy. So I I go ahead and specify that my polynomial is of a general polynomial degree 3, and I'm just specifying it in power form. Okay. And now I can set up 4 equations in 4 unknowns, the coefficients A0, A1, A2, and A3. So the first 2 equations are what we've seen from polynomial interpolation anyway, where you require that by substituting x naught and x1 into a polynomial, you get the corresponding y values, y naught and y1. But the third equation comes from a derivative of a polynomial evaluated at x naught, and then the fourth equation comes from the second derivative at x naught. So now we have 4 equations, 4 unknowns. We can go ahead and solve this system. But this can be expensive. If you have a polynomial degree n, it takes order n cubed operations to solve this system of equations. Also, if the distinct x values are close together, the matrix may be very ill-conditioned. So it has the same problems with the very first approach I showed with polynomial interpolation, where you're solving a system of n plus 1 linear equations and n plus 1 unknowns. So for regular polynomial interpolation, we already have 2 other approaches. We have Lagrange interpolation, and we also have Newton interpolation. So, and it turns out to be easiest to work with Newton form. But here's how we do it, because you have to take into account that we're trying to match derivatives. So here's what you do. Suppose you have a point xi, and you are specifying its y value, y prime value, y double prime, so up to a certain order derivative. However many conditions you impose on it indicates how many times you list it in the divided difference table. So in your divided difference table, the first thing you do is you list your x values, and then you list your corresponding y values. So now you're listing the same x value multiple times. I'll show you an example momentarily. Now, because you're listing x values multiple times, you may have a situation like this where you're computing divided difference, and the x values in your denominator are the same. So what you do in that case is, so you can't compute this directly, you fill in the derivative value. So if these are just function values, so this is a first order divided difference, then you substitute the value of the first derivative, because that's something that's known, because it would be specified. And then for a higher order divided difference, you're filling in a higher order derivative. Oh, that's a typo. Okay. Yeah. So you have to remember to divide by the appropriate factorial. So whatever order derivative you have, you must divide by that factorial in your divided difference table. Okay. Yeah, do a divided difference table example with, okay. So that's for something else. I want to have a divided difference table for this one. Well, for this example right here. So where I have x naught and x1, and x naught I have these 3 conditions. Okay. Now, okay. Oh, sorry, I put this in the wrong place. All right, so in this case, I want to show you what the phi difference table looks like. Now, it's going to be interesting trying to do this in the fly in LaTeX, but so before. So I'm just exacting up and giving the colors pinwheel of death here. Those things are not fresh now. Don't do this to me. Okay, yeah, you can't see the pinwheel of death on the screen, but now I can't even get back to that app. Okay, I'm gonna have to do a force quit. Dang it. Okay, let's try this again. Hopefully I didn't lose all that content. Okay, I didn't. All right, start sharing again. Okay, let's hope it goes better this time. Oh, doing it again. I can't believe that. Oh. Okay. All right. I guess something I'm doing here is confusing it. So I think what I'm going to have to do. All right. I'm going to try something different here. Well, I'm going to go to another app and start it, and then and hopefully I can continue in the same editor. Sorry about this. Technology is not my friend today. How many columns do I need? 1, 2. We have 4 coefficients of x. 1, 1, 2. Okay, let's try this again.
Not my fault this time.
What?
Not my fault this time.
Okay.
Technology failed.
Okay, so the part that wouldn't like me typing before is in there. Let's see what happens. Okay, so first I'm going to list the x values in the first column, and because I have 3 conditions, on x naught, I have to list it 3 times. And then I only have 1 condition on x1, so I'm only going to list it once. Okay. All right, now the second column, I will list the y values. So since x naught is listed 3 times, its y value will also be listed 3 times. At least this thing is working now. And then for x1, I list its value y1. Okay. Now, the next thing I'll do is I need the first order phi differences. So what I do is y naught minus y naught divided by x naught minus x naught. But that's where you fill in the derivative in between. So I would have first derivative is z naught. Here again, y naught minus y naught divided by x naught minus x naught, that will be replaced by the first derivative, z naught. Okay. Now here I have y1 minus y naught over x1 minus x naught. That divided difference I can do regularly because these values are distinct. So I can go ahead and compute that divided difference with no problem. Okay. So I'll fill that in there. Okay. I'm going to make that a fraction. It doesn't take up so much space. Okay. All right, so now this column of the first order divided differences is complete. Now I go to the second order divided differences. Here I'll have z naught minus z naught over x naught minus x naught. So that calls for the second order divided differences calls for a second derivative. So that would go here. Second derivative is specified to be w naught. All right. And then this divided difference is no problem. We're dealing with distinct x values. From a formatting point of view, it's going to be a bit of a pain. So between x. Right, so this goes here, so on the same line as the third x naught. Okay. So that's going to be so this divided difference. All right. Minus this one, minus z naught. And then all of that has to be divided by
Hermite interpolation.
by x1 minus x naught. Okay. Now, there's one divided difference left. That would be this minus this divided by x1 minus x naught. I'm not doing that one. Okay. Well, I'll write out what it would be, like the general notation for divided differences. X naught, x 1. Okay. So now, once you compute all of these, then, as before, with the Newton form, you can go down the top row of divided differences. So in this case, it's third degree, so it's P3 of x is equal to y naught plus z naught times x minus x naught, the first center here, plus w naught times x minus x naught and x minus x naught again, so x minus x naught squared, plus this third order divided difference, times x minus x naught cubed. So you're still using these centers, except in osculatory interpolation, you have points repeated, so you're going to have factors of powers greater than 1, like you see here. Okay. But the procedure for how you form the interpolated polynomial from the divided difference table is exactly the same as in Newton interpolation when all points are distinct. Oh.
Do we need factorial?
Yes. I was just catching that. I forgot.
Factorial.
There, 1/2. So for example, if I take the derivative of this, with respect to x.
Also the polynomial.
What?
Division of a W naught.
Oh, yeah, right there. Okay. So if I take the derivative of this, then that term would go away. I'd have z naught. And all of these would have at least one factor of x minus x naught, and then plug in x naught, so those terms go away, and I'd have that be left with z naught. If I took the second derivative, all this would go away. The second derivative of this would be w naught, now that I have a factor of 1/2 in here, to cancel with this 2. And substitute x equals x naught, and I get w naught. All right. Okay. So questions about how this polynomial was obtained? All right. And we're going to see another example later. Also, we'll use a divide difference table. Okay. All right, now, during the rest of the time, we'll talk about one particular type of oscillatory interpolation, and that's called Hermite interpolation. So the idea in Hermite interpolation is that for every single distinct x value you have, so x0 up to xn, so these are assumed distinct, but you have two conditions on each point. So for each one of these x values, you specify the y value to match and the y prime value. So here you have n plus 1 x values. You have two conditions on each one. So you have a total of 2n plus 2 conditions to satisfy. So the polynomial you're going to get, the Hermite interpolated polynomial, will have degree 2n plus 1, as opposed to degree n, when you only specifying the y value. Now, here is the error formula for regular interpolation, which I'm referring to as Lagrange, that I showed you on Tuesday. Here's the error in Hermite interpolation. So here we have degree n interpolating polynomial. Here, in the Hermite case, is 2n plus 1. So notice the similarities and differences between the two. So whatever degree the polynomial has, that plus 1 is the order derivative. You have that degree plus 1 factorial down below. And then you have these factors, x minus each of the interpolation points. Now, here those linear factors only occur once, because all the x values are distinct. Here, they're all squared, because each one is listed twice for the two conditions that it has to satisfy. In fact, if you took this error formula, and if you had pairs of points that were still distinct but close together, but you let them converge to each other, each pair, then this is exactly what you would get in the limit. So, now I'll show an example of how you do divided differences for the Hermite case. So once again, I have two distinct x values. I specify the function value and the derivative values at each point. So I have two distinct x values, but a total of 4 conditions. This is an example of a function that would satisfy all 4 conditions. It's certainly not unique, but it could be something like this. So what I do is I define these new variables, z's, z0, z1, z2, z3, and these are, I set them equal to the x values, taking into account that each x value is listed twice. So these are not distinct. And then I construct my divided difference table using the z values. So here, this is just my index. Here I have each distinct x value listed twice. Here I have a corresponding y values. They just both happen to be 0 in this example. Then, for my first order divided differences, when the z values are equal, I fill in the derivative value. So in this case, it's 1 for both points. Here, this divided difference, in the middle, I compute in a regular way, because the z values are distinct. So it happens to be 0 in this case. And then, after that, there are no more derivatives to fill in. It's only first derivatives when it's meet. So then I compute the remaining divided differences in the usual way, and this completes my divided difference table. So now, I can fill in the polynomial. It's unfortunate that it's on another page. See if I can do something about that. Okay. I'm going to eliminate some spacing here. Oh, I was hoping it would bring the polynomial back, but it did not. LaTeX does not want to cooperate with me. Okay. Actually, I think what I'll do, I'll remove this. Okay. There it is. Okay. So, in this case, I have a third degree polynomial because I have 4 coefficients in total. So, I go across the top row, and I fill in my divided differences. 0, 1, minus 1, and 2. First term has x minus z naught, and then I have x minus z naught, x minus z1, and then x minus z naught, z1, z2. So again, this is exactly the same procedure when it's regular Newton interpolation, when all the listed values are distinct. So now I just fill in all my divided differences and all my centers, and work at the polynomial, and this is what we get in this case. Remember, whether it's regular Newton interpolation or this Hermite case or any other oscillatory case, if you're using the top row of divided differences to construct your polynomial, then the last center will not be used ever. So those even in the highest degree term, we have x minus z0, z1, z2, but there's no x minus z3 anywhere in here. So keep that in mind, because otherwise the polynomial would not have a correct degree. This is on the midterm. There's a problem involving divided differences. Not the Hermite case. It's important to be able to go through a process of filling out the table and then using those divided differences to construct a polynomial. All right. So, are questions about this case? All right, this is a good break point. All right. Now, with a regular polynomial interpolation, we've had a Lagrange form and a Newton form. For Hermite interpolation, I've only shown you a Newton form. So now I can show you a sort of Lagrange-like form for the Hermite case. compare Lagrange form, where we represent Pn as a linear combination of Lagrange polynomials, where coefficients are the function values. Okay. And where Lagrange polynomials have these key properties. If I take polynomial j and substitute in xj, I get 1. And if I substitute in any other x value, then I get 0. All right. So, what's the corresponding form in the intermediate case? It's going to be a bit more complicated. So, that polynomial, h2n plus 1, then we take into account f values and f prime values. So what we have are, so f times these polynomials h, 2n plus 1 is x, we give them an index, right? Plus f prime values are needed here too. And these polynomials are called k's. All right. So we need to make sure that if we substitute in one of these x values, we get the appropriate f value. We also have to make sure that if we take the derivative of this and we substitute in a certain x value, we get the appropriate f prime value. So that criteria leads to criteria for this currently unknown polynomials, the h's and the k's. So first, the conditions that the h's have to satisfy is similar to Lagrange. So if I have a jth polynomial and I substitute in xj, I need to get 1. If I substitute any other x value, I need to get 0. So that is just like Lagrange. Okay. But then, what if I take the derivative of this whole thing? And therefore I have a derivative of these. Well, I need these polynomials to have their derivatives equal to 0 at all the x values. Because I never want these to appear in a derivative, only these. So I must have h the derivatives must equal 0. All right. So this condition is for I not equal to j. But this condition is for all I from 0 to n. So now I have, here I have n conditions. Here I have one more condition, so a total of n plus 1. And then I have n plus 1 more conditions here, so that's a total of 2n plus 2 conditions, which is enough to determine the h's uniquely. And now I have similar criteria for the k's. But here it's for a derivative. Oops, the prime in the wrong place. Okay. Here too. And then the k's are equal to 0 at all of the x values. So in terms of where you take a derivative or not, it's opposite between the h's and the k's. So based on these criteria, we'd like to be able to come up with formulas for these. And it turns out that the Lagrange polynomials will help us do that. Now, because for one thing, if you take a look at the h's, for instance, when I is not equal to j, h is 0, and h prime is 0. So we have n points at which the polynomial is 0 and its derivative is 0. Well, those roots, which are all xi, I not equal to j, those are the roots of Lagrange polynomial, which is also 0 at those same points. So let me write that down. So that's equal to 0 for I not equal to j. And we also have h, polynomial j evaluated at xi, and its derivative at xi, and k and its derivative. Alright, so that means that for polynomial number j, xi is a double root for both the h's and the k's. And since those roots are the same as the roots of this corresponding Lagrange polynomial, what that tells us I can say the following, that I can describe the h's as having the Lagrange polynomial squared as a factor times some other polynomial, which I'll call pj of x, which has degree 1, because Lagrange polynomial is degree n. Squared is degree 2n. But the overall degree has to be 2n plus 1, so we only have 1 degree left. So this is a linear polynomial that has 2 coefficients to specify. And the same can be said for the k's. That's equal to the Lagrange polynomial, the same index squared, times some other first degree polynomial. Okay. So most of the job is done now, because these conditions are satisfied, these are satisfied, these are satisfied at least for I not equal to j, these are also satisfied for I not equal to j. But we still have to deal with this, these two conditions, and then these conditions for a case of I equal j. Okay, so let's take a look at those 4 conditions. So for one thing, when I substitute in xj, well, that's going to be equal to this at xj But the Lagrange polynomial at xj is going to be equal to 1. So it's just pj of xj. And that has to equal 1. So this is one condition. But then when I take the derivative of the same function and also plug in xj, all right. Now I've got to take the derivative of all this. So that's going to be by product rule. Okay, so I have 2 times Lagrange polynomial times its derivative times this, okay, but plus Lagrange polynomial squared okay. Now to simplify this as much as we can, well, that's 1. This is known to be 1 from the other equation. Okay, so I'm just going to copy this and simplify it. Okay, so I have, that's 1. All right, the prime I do not know, else I believe it as is. Okay, and then that is 1. Okay, so now this is a linear function, so now I know the slope. Okay, so now these two conditions are enough to determine Pj completely. X, that has to equal 1 plus 1 minus 2 prime. Oops, my subscript is off. Times x minus xj. All right. And actually have the final formulas worked out in the book, and I'm comparing. Yep, okay. All right, so that's how you get that one. But then you have similar conditions for the case. So if I take k, j polynomial at xj, and that's equal to Lagrange polynomial squared at xj times qj of xj. Now, this is going to be 1, so it's just qj of xj, but that has to be 0. And then the last condition, okay, so I'm just going to copy this line and fix it. Okay, so all right, that's qj of xj, and then we have q over there, and then part. All right, now
Become case.
hold on a second. That has to be 0. Okay. Yeah, somebody didn't take over. All right. Whereas this one has to be 1. Okay. Okay. All right. Now, okay. So So this is 1, we don't know what this is, but this is 0, so this whole term goes away. This is 1. So this just reduces to qj prime of xj has to be equal to 1. So qj of x is equal to just x minus xj. So that will turn out to be simpler. So putting it all together, so the h's equals the Lagrange polynomials squared, okay, times 1 minus 2 Lagrange squared times x minus x j. There, it's done. So these lead to a Lagrange-like form for the polynomial, but that would have the same disadvantages computationally as regular Lagrange would. For instance, if you're adding interpolation points, then all of these polynomials would have to be revised. And plus, even higher degree now, so it's even more work. So I would still recommend using the Newton approach. From a coding standpoint, it's a whole lot easier. But I want to show you both perspectives, just as we have Lagrange and Newton in the distinct case, and we also have that in the oscillatory case. If you have a different kind of oscillatory interpolation, like not non-Hermite, where you might have like second derivative specified, then creating polynomials like these would be even more difficult. So I'm not even going there. Okay. All right. Now the homework for this section is not due for a while because we have a midterm coming up. So you'll be returning to this then. Next week is all about the midterm. Review on Tuesday. Thursday class will not meet, but I will post it around that time. And I'll send out a message early next week, reiterating the particulars about the midterm, as far as like the time frame and all that. Okay. Now, do we have any questions about any of the assignments, upcoming midterm? And I'll be using Tuesday to talk about the practice midterm and anything else midterm related. But any homework questions? We should take a look at there.
If you post the midterm, are you just going to post like a PDF similar to the review?
Yes.
Review? Okay.
Actually, here's what else I'll do, in case some of you might want to work with this. So when I post the PDF of the midterm, I will also post the .tex file, so that if you want to work your responses into that, as I've stripped out any comments I made that reveal answers. So.
Or don't.
That's right. One thing I want to mention real quick, because this week faculty are required to post interim grades for everybody. It'd be nice to have a midterm included in that, but they like the midterm grades earlier. And I have noticed that there's a handful of students who have not yet submitted anything, homeworks or quizzes. So I fill in something for interim grade. I didn't put an F, but still not something that people would like. So But and the thing is, yes, I openly admitted that I'm being flexible with time getting assignments in, but we're several weeks in, and that's a lot to catch up on. So I don't know. I would hope that because we have like on average like 12 or 13 students who are either attending here in the classroom or are attending the virtual meeting live during class. But that means at least a number of people who are doing neither. And I'm hoping that they're watching at some point and keeping up with things. But if you haven't turned anything in, I would encourage you to change that. And well, even if you haven't done that, at least you're doing what you can to prepare for the midterm and watch or participate in the review on Tuesday, because each individual homework assignment may not count for much. Like I said, it's roughly 1.5%. But the midterm does count for a lot. It's 30% of the grade. So, if you're not really planning to continue class, but you still have to be registered, then it'd be a good idea to withdraw. But I'd not prefer that outcome. But yeah, please do what you can to keep work coming in, and I'll just keep rating things as they come. All right.
Professor, shall we do the previous slide?
Oh, I don't have it on the schedule.
So we finished the interpolation.
Yeah, we have. Yeah.
Professor, for the midterm, how is the submission going to work? We just send you a file?
Yeah, so I'll upload something to campus. Yeah, just like the other stuff. All right, if there are no questions, then there we go.